Welcome to MyProjectBazaar.com. Now we discuss about the product for energy efficient approximate multiplication for digital signal processing and classification applications. Next we see the abstract for the product. Achieving high energy efficiency has become a key design objective for embedded and mobile computing devices due to their limited battery capacity and powerful budget. To improve energy efficiency of such computing devices, significant effort have already been devoted at various levels, from software to architecture, and all the way down to circuit and technology level. Embedded and mobile computing devices are frequently required to execute some key of digital signal processing and classification applications. To further improve energy efficiency of executing such application, first, dedicated specialized processors are often integrated in computing devices. It has been reported that the use of such specified processor can improve energy efficiency and compared with general purpose processor at the same voltage and technology generation. Second, many DSP and classification applications heavily rely the complex probabilistic mathematical models and the design to process information that typically contains noise. Thus some computational errors they exhibit graceful degradation in overall DSP quality and classification accuracy. Instead of a catastrophic failure, such as the computational error tolerance has been exploited by trading accuracy with energy consumption. Finally, these algorithms are initialized, designed, and trained with floating point algorithmic but often converted the fixed point arithmetic due to the area and power cost of supporting the floating point units in embedded computing devices. Although the conversions process leads to some loss of computational accuracy, it's not a notable affect the quality of DSP and accuracy of application due to the computational error tolerance. The need to support the various digital signal processing and classification applications on energy constrained devices has stability growth. Such applications often extensively perform matrix multiplication using the fixed point arithmetic while exhibiting tolerance of some computational errors. Hence, to improving the energy efficiency of multiplication is crucial. It's a brief. We propose the multiplier architecture that ground the trade of computational accuracy with energy consumption at that time, compared with the precise multiplier, and the proposed multiplier can consume the circuit complexity and all those more things to be ever. In this brief, we propose the approximate multiplication technique that takes the m consecutive bits for each n bit operand when m equal to the greater than by n by 2. An m bit segment can start only from the 2 or 3 fixed bit positions depending on whether the leading 1 bit located to positive number. This approach can provide the much higher accuracy and simplify truncating the LSB and to identify the overall approximate architecture for inbuilt-in DSP based systems. This is our flow diagram for the product. First we select any one of the given input ECG signal to be browsed, then to apply the filtering function. This filtering function to filter the given selected input ECG signal and to apply the low pass filter for using the filtering function and to write all the values to the text format. Because Xilinx only used into the integer values, so we write all the values to the text. These functions to be presented in MATLAB 2013 A software and to apply the MATLAB file to Xilinx software and to call the Xilinx software directly and to identify the QRS deduction based DFT feature extraction architecture. This DFT feature extraction architecture mainly used to the approximate multiplier functions and to identify the Gaussian kernel unit using the approximate multiplier. The approximate multiplier to identify the DFT feature extraction and the approximate multiplication function, then to pass the Cardic and exponential architecture. The Cardic based exponential based architecture is used to identify the exponential processing element using the Cardic architecture. The Cardic architecture to reduce the number of rotating function in our exponential processing element architecture. The kernel identification unit is used to identify the minimum distance value for overall test vector and support vector values. Then to passing the scaling unit function. The scaling unit function is used to identify the overall data-based support vector and pre-processing for all the support vectors, and to set the any threshold value, to set the minimum threshold value for the given input vectors and the test vectors. Then the test vector and the given input support vectors to be compared with minimum threshold values, and to identify the satisfy the condition to be yes and the not satisfied condition to be no. The not satisfied to be analyzes the another one data. If the condition is satisfied, to passing the this data to be label. The label to be identify the which type of disease to be presented in overall input ECG signal based on our QEC detection process, and to identify the QEC detection process and compared with the overall database, and to finally life threatening result for our required simulation window. These functions are all the present to be Xilinx 14.2 software. This is the final process for our overall architecture. We use the approximate multiplier for these three functions also. Finally, we see the output for the product. First, we run the main function to be run and select the any one of the ECG signal for overall data set. We select the one of the data set and to select selected signal to be displayed, and to limited signal to be generated. This is our the selected limited ECG signal without noise. We apply the low pass filter and remove the noise, and to write all the values to the text, and to apply the input for the Xilinx software, because Xilinx software consists the only integer value to be presented. So the inputs are presented from the MATLAB and to process the our overall architecture. Then to simulation window and to simulate this simulate model. The simulate behavior model to be separate presented the overall simulation process. This simulation process after completed the simulation window to generate the ISIM project navigator file. This navigator file is used to represent the simulation purpose. This is the given ECG dataset for overall architecture signal. Run all the data and to finally generate the output data status, ECG data status. Then to apply the clocking signal and to create this signal level to be analyzed. And finally we classify the which type of the signal life threatening arrhythmia type is calculator. Then to apply the one and run. And finally we identify the signal level. Arrhythmia is a bradycardia or apticardia or the normal signal. So the signal to be normal, to be identify the final classification process. This is our the classification process output for overall architecture. This is the final output for the product.